Now we are recording. So if we go back then, and yeah, just I mean, the previous time we had a very good Q&A. There were no people talking at the same time problem at all. So I think this could work really fine. I don't know if you can raise your hand here in this WebEx, but I guess you can. Yeah, I think we will figure that out. We had a good discussion last time, and we also had some Q&A in the chat. And when you talk for the first time, if you want, please introduce yourself. It would be nice. Yeah, I think that would be my intro. Any logistics, questions, comments, or things before we start the presentation? Okay, then we hand over to Mark, and please, Mark, start your presentation.
Okay. Let me try and share.
Perhaps I don't know if I need to stop sharing. I have no clue. Oh, here it comes.
I'm not quite sure what I'm sharing.
You are sharing your PowerPoint. Yeah, now you're sharing the full screen, so now it looks perfect.
I'll probably stay sharing the full screen. It probably makes most sense. If everybody would like to mute, but Ola, could you keep your eye on the chat and see if people ask questions and voice them if they do, so that
yeah, sure,
they get through, because I can't see the chat and see the, apparently I can't see both at the same time. Before I get going, I'd like to reiterate what Ola said as well. If you've got ideas for the SystemC Evolution Day this year in October, please submit them to us. Ola said it, I'm just saying it again, just in case you didn't hear it the first time round. We could do with those ideas. Okay, so a lot of questions got asked about SystemC and QEMU recently, and a lot of people said, you know, Mark, it might be a good idea to do a little presentation to this group about what's there and what's available. I think I did a presentation 3-4 years ago now at a DVCon. I guess things have updated a little bit and moved forward a little bit. So this is by way of a refresher and to explain kind of what's in the box. I'll take it relatively slowly. I'm not going to go into too many details, but we'll address a few. So first off, I'm assuming most of you have heard at least of QEMU and might have some interest in it, but just a little kind of brief potted history. It's an old project now. It's been around for quite some years, and it is probably the de facto standard in terms of virtualizers. It's fast. It has an awfully large number of people contributing to it, including some of the big names in the industry. So it's pretty well supported. And now, thanks to us, it has a few features in it which are quite useful in terms of EDA in general. So that's what we'll kind of come on to. First off, a lot of people ask, so what is supported? This is the list as of May. So version 6 of QEMU was released earlier this year, and this is kind of what's officially in the official repos. So you can already see that there's an awfully large, long list there. There are a number of other off-tree repositories available, including, for instance, you know, we've just done some work for Calray, amongst others, and there are other repositories out there as well, which cover other architectures. Some of them are more or less up to date with the upstream tree. There are 3 columns here. The first column is kind of a bit weird, and you probably don't need to worry too well. We'll come on to KVM. We will come on to KVM later. So let's talk about that in a minute. The TCG guest is, if you like, the bread and butter of what we need. It's the thing which allows you to execute a CPU, if you will, in your virtual platform. And then this thing, MTTCG, we'll come on to later as well. It's the thing that we've added to make it so that it runs significantly faster for multi-core. But the key one is the TCG, and obviously, if it's not supported by TCG, it's not in QEMU. So by default, all of these are yes. So we've done a couple of things over the years to make QEMU just that little bit more friendly. The first is this thing, multi-threaded QEMU or multi-threaded TCG. Second is obviously the integration itself with SystemC. And the third is that we've added a number of mechanisms to count various different things. I mean, there's instruction counting, but there's also cache access counting and things like that, which we'll talk about in a minute. One key thing about QEMU, we always get the question, and everybody gets the question, how fast is it? Very approximately, at least for TCG, very approximately, one guest instruction requires about 15 host instructions. So that means if your host is running, I don't know, 4 or 5 times faster than your eventual target, you can do the maths yourself, but you don't get, you know, it's not a million miles away from real time in the end. Okay, so that's QEMU. So it's great. Why not just use QEMU then? It seems to be set up, it works, it's open source. It's great. Well, it's not standard, and being a true believer in the standards, I think it's probably quite good to use the standards. It changes all of the time, which means that if you start developing on QEMU today, then in a year's time, you're going to have to revisit what you've done and update it. And a lot of people don't do that, and a lot of people don't consider that as part of the kind of the deal, if you like. And in the end, that means that their model falls off the tree, and then other people can't use it, and so on and so forth. So yeah, there's an awful lot of updating that you need to do. And there are changes, there are even fundamental changes to the way the QEMU object model works internally and other things too. And you can't, it's written in C, but it's written in a sort of a kind of C++-y like C. And you kind of have to know an awful lot about what's going on inside QEMU to write a half-complicated model. Simple models are always simple, but when you get to writing something a little bit more complicated, you end up having to know quite a lot about QEMU and how QEMU works. And that can be a bit painful. So hence the kind of elegant solution, if and when it's possible, would be, well, why can't I use SystemC and have all of those complicated things hidden away behind sockets and what have you. And that's basically what we do. And the thing then, of course, is, well, actually, inside QEMU, there are an awfully large number of CPUs, but there are an incredibly large number of devices. And some of those devices are quite complicated and would be really valuable to reuse. So you want the same solution, if you like, to be able to be reused for both the CPU models and the existing QEMU device models. So effectively, what we're looking to be able to do is to treat QEMU as kind of a repository of very optimized CPU models and other device models that we could then pull into a standard TLM environment. So that's what we've got. Now, I mean, I don't particularly want to talk about green socks too much, but I mean, this is open source, so people can go look at it. I'll come back to how to get hold of that later, because that's not so easy right now. But it's you can do the similar sort of things yourselves. It's just that we have a version. So I'll explain how this works. And we call our version QBox. And basically, yeah, you can understand why we would do that.
Mark, there is a question from David Black if you want to take it now.
Sure, go for it, David.
Yeah. How many distributions or variants of QEMU exist? Or does everybody play nicely and just have a single central model?
So there are lots of forks of QEMU all over the place, and there's a lot of off-tree work that goes on for different things. But there is a very strong recognition that upstream is upstream. There is only one upstream. And the reason why you care about that is that if you build your own fork, you are responsible yourself for maintaining it and making sure it still works. If you get it upstreamed, then the community at large will make sure that when they add stuff to it, they don't break your thing. And that's critically important, right? I mean, as things get developed, you want to make sure that things don't break. So those who are deeply involved, I mean, for instance, Xilinx, I don't know if we've got anybody from Xilinx on the call, but Xilinx, some years ago, I believe, made a statement that said, you know, we will make sure that as many as possible of our devices are available as QEMU models. They do that, we help them a lot doing that, but they also have an off-tree branch where they hold things that are not yet upstreamed. And they work incredibly hard to get those upstreamed, because otherwise I mean, it's just a huge drain on resource otherwise to maintain those models. So that's why people try to upstream as much as possible and don't fork and just wander off into the bushes. I am unaware, I mean, there are a number of forks of QEMU where they have decided I'm wandering off and I don't really care what happens upstream. But those tend to be not so well used and not so well maintained forks. Does that answer your question, David? Jolly good. So a little bit of history, if you will, about where we've come from in all of this. Many years ago, we tried this first off to wrap SystemC models into QEMU. And that was kind of a good first attempt, good idea. It meant that, for instance, I mean, at the time, we had I can't even remember what we called it, but we had a way in which you could build a PCIe kind of model and plug it into into QEMU. And that, for a class of model, that's really useful, right? And you didn't have to worry about having two separate simulators or anything. You basically just had the SystemC model wrapped up into a QEMU model. So that was kind of attempt number one. Attempt number two was exactly the opposite, and that was, well, why can't we take a QEMU model and wrap it into SystemC? And attempt number two survived a lot and did well and was kind of quite useful. And I think that's probably what I demonstrated last time round at DVCon as well. And attempt number two basically kind of exposed a TLM2-like interface into QEMU. Attempt three, which we're kind of now in round three, the plan here is to expose much more of the internals of QEMU's structure into SystemC. And the reason we want to do that is because we want to be able to not just use the CPU, but ideally, if we can, we want to be able to use some of the other models inside QEMU as well. So we have a way in which we can expose that QEMU internal structure into first C++ and then into SystemC. That enables us to wrap up a CPU pretty easily, but it also enables us to extract, if you will, some of the other devices and to have those connected. And that gives us a more flexible way of integrating QEMU and SystemC. So that's kind of where we are today. They're looking at David because I can see his face and I'm worried that he's about to ask me a really complicated question. I'll keep going until Ola interrupts me. Okay, so what does that actually mean? It means that individual components, in our case, are exposed as TLM2 models. Actually, behind the scenes, we do some magic wiring to make it so that effectively, for instance, if you have a device model and you've chosen a QEMU device model and you have a QEMU CPU, the QEMU CPU will essentially do a DMI access and discover that the thing at the other end is its own. And in doing so, it will connect the things together, join the dots, if you will, and make the whole thing play nicely together, and give you the performance that you'd expect out of a pure QEMU model. So there's no performance degradation here. The magic happens behind the scenes, but the user gets to instance these models just like any other TLM model. So that makes their life, the user's life is nice and easy. So we can have QEMU instances with CPUs and devices. We can also have multiple QEMU instances, so that you can have several different clusters, for instance, of CPUs. Now, QEMU itself, recently, I think in the latter versions of 5 and now in 6, allows you to have heterogeneous cores within a single QEMU instance. So that's kind of interesting as well. But our thought here is sometimes it's quite convenient to separate the things out, particularly it's all very well having separate heterogeneous instances, but actually constructing the bus fabrics within QEMU to be able to represent the sort of heterogeneous fabrics that you know, heterogeneous cores and their fabrics that you'd normally see in a device is tricky. So in general, probably it's easier from the perspective of people using this to simply be able to build their fabric in SystemC and connect it together as, in this case, separate QEMU instances.
A question here, Mark, also from David. We talked about devices in contrast to CPUs. Do you have examples of devices that you have successfully made visible in SystemC?
So yeah, I mean, actually, there's a bit of formalism in terms of what's considered a CPU and what's considered a device inside QEMU, but that's not necessarily a helpful formalism. Inside SystemC, yeah, so we've exposed everything from your simple UART through to Ethernet controllers, and indeed there are VirtIO controllers now as well. We have a PCI. What's it called? A PCI? Oh, they've got that funny name, bridge, not bridge, whatever it's called, thing that allows you to connect up PCI and then like an NVMe or something like that behind it. So all of those things are exposed as SystemC objects. Obviously, GICs and timers. The GIC can be particularly nasty, obviously, and has to have some special relationship with its core. So it's particularly convenient to have the QEMU GIC available in the platform. Does that answer the question?
I was curious about multi-threading because you mentioned it before. Do you plan to come back to the topic of multi-threading?
I do.
Okay. Good.
Let's take it when we get to multi-threading. I just wanted to re-emphasize that from the perspective of a user using this stuff, these models just look like TLM2 models. They have the same TLM2 ports on them and so on and so forth. When you instance a QEMU model in our framework, at least, you have to give it a reference to a QEMU instance. But apart from that, you look at it and you squint and you go, that's just a TLM2 model. It's just got TLM ports on it. It might even have SC wiry type things on it as well. That's a separate discussion as to whether they should be SC signals, SC wires, or what, but yeah, everybody has their own one of those, and that's probably the topic of another Fika. But yeah, we have our own, and that's used for interrupts, for instance. But yeah, all of the sort of standard SystemC framework and fabric works around these models, and indeed they expose CCI parameters. So they are just TLM models. And
there is a question from Jakob about do you run everything inside a single process? But I guess we can take it when you come to this multi-threading thing.
The answer is no, and we'll take it when we come to the multi-threading.
Okay.
No, except. Okay, so yeah, we'll take that when we come to the multi-threading. The other thing that I wanted to point out here is these models are also interchangeable, right? So we have customers who use, for instance, an ARM fast model, and will happily have a build time configuration parameter switch backwards and forwards between QEMU and the ARM fast model, because the ARM fast model is better in certain situations and the QEMU model is better in others. And I don't think we need to go into why or when, but you know, just that's the way it is. And so yeah, these models are interchangeable TLM models, just like anything else. That turns out to be important when we get onto licensing later as well. I wanted to deep dive slightly, it's very pictorial, so it's not too much of a deep dive, into KVM. I said I would at the top, so I will. KVM and the TCG. So this is a picture or kind of graphic of how this whole thing works very, very simplistically for TCG. We have our host memory that kind of feeds into this magic tiny code generator, which recompiles the host memory and spits out essentially instructions for the guest. Those are then cached in some sort of cache of host code, and then the host code is executed. And if you get a load store, then there is some sort of a TLB site type of a thing that happens, and it might then access directly back to host memory, or indeed it might access a peripheral model. Okay, I'm hoping that nobody's too surprised. So what's KVM? Well, KVM simply says, well, actually, those instructions in the host are exactly the instructions I need to execute anyway, because I happen to be sitting, I'm an ARM and I'm on an ARM, or I'm an x86 and I'm on an x86. So all KVM does is remove that tiny code generator and that local cache and execute the thing directly. There's still a TLB, there's still a possibility to access other models. So the upshot of all of this is that were you to want to, you would run one of these things and you would end up being able to build a virtualized machine, which would keep you completely isolated from the real machine. That's why Red Hat and Co. are so deeply involved in the QEMU project, because KVM is part of QEMU and KVM is a critical part of their infrastructure for this reason, to virtualize. It's one of the virtualizers they use. So, you know, there's an awful lot of cloud based on this stuff. So that's why the project kind of has really rather larger legs, as it were, than just the EDA community, if you like. But it also means that there are lots of other models and things, because people come along and say, oh, well, I'd really like to have a Verto graphics processor or something like that. And then all of a sudden people need to make sure that thing works. It also means that, for instance, it's something that we've not done an awful lot with, but we probably should. There's a lot of work being done on migration, which means that at the moment you can live migrate a KVM machine between two different hosts. That could end up being really, really interesting from the point of view of doing save and restore, for instance, and other things.
About KVM, you said it's about the instructions that you run x86, you run them natively because you don't need to translate. Then there is this other thing. I don't know if it's called VertIO or what it is, that you, instead of having a model for a PCI controller, you decide to use the real one in the real machine. Is that part of the KVM concept, or is it something else?
Absolutely. It's not. Yeah, actually, VertIO is kind of, it's kind of weird, and it kind of has different flavors. But basically, I mean, a very simplistic view of it is it's yet another model. It just happens to be a model which is kind of tuned such that the device driver in the host can access it very directly. And in doing so, you kind of pass through, kind of, as it were, directly from the host through this VertIO thing, and then the back end, as you say, might be implemented on the host as well. So it's a very thin layer, and the idea there is to make it as efficient as possible in this sort of environment. But from our point of view, I mean, you can consider a VertIO model as being just yet another standard device. It's just its interfaces on both sides are kind of tuned to make it easier to integrate and easier to use. So the other question, the other thing that we were going to talk about was multi-thread. Actually, I've got another slide on multi-thread as well, which I'll come back to, but this is just to give you an idea about how multi-threading is working inside QEMU. So here, this is a choice, right? And the choice is essentially, I mean, this is where Jakob's question probably came from. The choice is essentially between having something deterministic and having something non-deterministic. As soon as you bite on the non-deterministic bullet, then you can have, for instance, in QEMU, a host thread per CPU. So say you're wanting to execute 4 ARM A53s in parallel, very typical. You could have 4 threads doing that, and assuming that those things are well used, then you'll get a 4x performance improvement. However, as QEMU stands today, you have thrown away any notion of determinism. So there's a use case where this is good, and obviously there are lots of use cases where this is bad. The use case where it's good is you're writing application code on top of this thing and you just don't care about determinism, you just care about speed. Seems that a lot of people are in that camp. Other people need the determinism. So in our case, you know, you switch on or you switch off, and you pays your money and you takes your choice. But within QEMU, you're allowed to have as many cores and as many threads. Well, you can have a thread per core. So that's one part of the multi-threadiness. And that thing is called MTTCG, and not multipath TCP, which is a completely different thing. Though I did have that mistake on the flyer on the introduction at some point. Okay, so just, you know, I mean, how good is that? This is kind of an old slide, but it's just a quick benchmark. Essentially, as the number of CPUs grows, the speed, the time it takes to execute decreases pretty linearly. There's a small overhead.
But this TCG, does it come with a locking machinery or concurrency protection machinery so that you don't mess up all your memory?
It comes with exactly and only the protection mechanism that the core has. So if you're going to write to some shared memory from core A and read from core B, and you have done nothing else, then good luck to you. If you've put load store exclusives or some sort of locking mechanism there, then that will work. QEMU itself will not, for instance, detect that you might have a problem there and shout at you. It will
Okay,
just
but
let
that's
you
the same
do
as hardware, right? So
exactly. It will let you do exactly what the hardware does.
Mm.
The actual semantics of the locking mechanism inside QEMU for ARM is similar, but not 100% the same as actual hardware. I'll leave that with you. The corner case is sufficiently remotely bizarre that it probably doesn't matter. So multi-thread. Effectively, if you think back to one of the earlier slides, I said we could have multiple instances of QEMU. Each of those instances of QEMU can be either in the SystemC thread or on its own thread. Each core inside QEMU can either be on its own thread or the SystemC thread. So we can lock the entire set of cores in coroutines on the SystemC thread, and they will just appear as coroutines in the one single SystemC thread. That'll give you a fully deterministic, fully serialized, if you like, simulation. Or you can have any number of QEMU instances with every number of threads inside it, which will give you a very highly parallel simulation, which will run very fast but won't be deterministic. Does that answer multi-thread questions?
And still, Jakob's question, inside a single process, I mean, we are still in one Linux process, but we have multiple threads, right?
We're still inside one single Linux process, but we have multiple threads.
And then there is a question from Jakob. So there is just one SystemC thread, or what?
We have, in our implementation, I mean, I know other people do different things, and I know Jakob, for instance, has multiple SystemC threads. We have one single SystemC thread, unless you fork inside that. The SystemC, obviously, you could spawn another thread inside SystemC. I mean, another P thread inside SystemC if that's what you wish to do. And we have components in our library which help you do that, but we don't parallelize SystemC ourselves. There's a library that does that. That's a different story.
But one SystemC thread, that I don't understand. One SystemC thread for this whole blue box, or what does it mean?
I think we have to be very careful about our terminology here. One P thread for all of SystemC. SystemC might have lots of SystemC threads.
Okay. That makes more sense.
Yeah. Okay. Just a little note on this whole determinism thing. Sorry to beat on about it a little bit. There is a thing inside QEMU called iCount. And iCount, when you use it, does what it says on the tin. It counts the number of instructions that a CPU or a set of CPUs execute. And you can use this to get determinism. It is intended as kind of a determinism on-off switch. And basically what it does is, I mean, it sets timers and things based on the number of instructions that have gone past, as opposed to anything else. If you switch the iCount mode off, you get wall clock time. So any timers that you have inside SystemC would then be based on wall clock. Obviously, in our case, we can put those timers inside inside SystemC and have them based on the SystemC time. But as so far as QEMU is concerned, if you don't have iCount on, iCount off means that you get wall clock time. Again, there's a use case for that, right? It looks really nice when you're running your operating system or whatever, and the clock seems to tick at the right speed and stuff like that. It's just feels nice. It's complete rubbish, of course, but it feels nice. It's a full sense of security. There's kind of, I believe, a missing link in this, which I'd like to see filled, and maybe one day we'll get around to it. At the moment, well, there's two missing things. Firstly, iCount at the moment, if you have multiple cores in your design, iCount will sum the total of the instructions in all of the cores in a serial fashion. That kind of is weird and wrong, I think. The second thing, which I think is kind of an interesting halfway house, is if you could fix that problem, you could also make it so that it would be non-deterministic, but you could have a kind of iCount come non-deterministic mode where you didn't use the wall clock time, you did use iCount time, but you used it with multiple threads. And I think that's actually possible and could have some interest in some situations. Like, I mean, it would give you a slightly more realistic impression of what the simulated time was. I'm not saying in any way that would be accurate or deterministic, just a kind of better than wall clock notion. So that, as far as I'm concerned, is currently a missing link.
We have a new question here coming in. It's from Karthik, and it's quite long. So perhaps if you want to speak, perhaps it's more efficient.
Sure. Hi, Mark. This is Karthik. So, the question is somewhat related to the current slide, but actually started in the one before. I'm trying to understand. I mean, I know that in QEMU, you can model, constructs like, let's say, watchdog timer. That is possible to be modeled. So when it comes to delays in QEMU versus time advancement and SystemC, is there any synchronization that is happening there? Is there anything that's going on there, or is it like a quantum construct in SystemC where you kind of allow QEMU to run ahead? How does that work?
Let me go on to my next couple of slides and see whether I've answered the question, and if I haven't, we'll come back to it.
Sure, thanks.
So yeah, the question then is, well, you've now described two notions of time. I mean, obviously there's SystemC time on one side and there's QEMU time on the other, at least. And I guess, as Karthik kind of noted back here, you could potentially have different notions of time in different QEMUs. You might have one QEMU that's using iCount and one QEMU that's using the wall clock, and you could have SystemC doing whatever SystemC is doing. It would be a bit of a mess. So how are we going to maintain a notion of time? Well, in general, in terms of TLM2, we thought we had this licked, right? We thought, oh, quantums, that's the answer. And we can dial the quantum bigger or smaller, and everybody should obey the laws and it should be fine. And the notion there was that each simulation would go until the end of the quantum. So simulation 1 would get to its end of quantum at time equals 20, and simulation 2 would take a little bit longer, and then when they got to the end of this quantum, they would synchronize. Okay. Different people ended up doing different things. I know that people use synchronization points and things, which is a very different way of doing things, which is probably a very different thing. But okay, that was the notion of how this should work. The issue is that if we've got things running in parallel, hence the kind of funny picture of, I think this is a slot machine. You put your pennies in and they roll down, and depending on where they fall, then the little horses move forwards, and the horse that gets the front first wins, something like that. And the question is, well, how do I keep all of these horses synchronized, particularly since they're moving in parallel? So in the old TLM world, the TLM quantum keeper was supposed to sit somehow between the TLM master and the rest of the TLM world, and it would allow the TLM master to keep running forwards until it hit the end of the quantum, at which point it would synchronize by essentially calling wait and allowing the rest of the SystemC TLM world to catch up. So some time ago, I mean, this is a long story, and I'm trying to make it very brief because there's a lot of discussion about this in the SystemC community, and I know that Laurent is on the call, and he owes me a telephone call on this subject. So Laurent, reaching out to you, you can come back and tell me about what it is that you've discovered on this at some point. The idea is that actually you could have these two different things in two different threads. So you essentially have two different time zones across two different P threads. And the quantum keeper would still be responsible for maintaining the synchronization between the two of them. So I haven't answered the question. All I've told you is where the answer is going to come from. It's going to come from that quantum keeper. And the quantum keeper is then going to need to have some mechanism by which it can either allow system C to stall, to stop, or stop system C because it's gone too far forward, or to stop QEMU because QEMU has gone too far forward. So one way or the other, it needs to kind of put the brakes on to stop the thing that's going too fast from executing too far forwards. So in reality, what that means is that we end up, I mean, this isn't actually a full list. This is kind of just the top 5 on the list. We end up with a number of different synchronization modes, if you will, for our quantum keepers. We can have a standard TLM mode where we have one thread of execution and it works the way TLM works and it's entirely deterministic. We can have a mode where you synchronize on every single event, which means that an event in System C is posted into QEMU and an event in QEMU is posted into System C, so they completely synchronize on everything, right? Obviously very slow, but in some situations necessary. We can have what we call a multi-threaded approach where we allow we allow QEMU to drift up to a quantum ahead of System C. And every time QEMU accesses System C, we notice the time difference and we allow either side to move forwards. And we allow that for potentially all of the cores in the simulation, which means that everybody is shuffling to move forwards at in the same time. And we can also allow what you would call free running. There's a kind of gotcha on free running. You can't be completely free. Particularly System C has to be prevented from drifting off into the way blue yonder. You have to maintain that System C is always behind all of the models. That's actually a law, if you like, given to us by the TLM standard, which essentially assumed that the CPU model would run ahead of System C. So this free running mode just basically says you can run ahead, but you can run ahead as far as you like, and it just makes sure that System C stays, as it were, behind, but keeps moving forward. And finally, I mean, another variant on this is to have a wall clock version where, as we said earlier, you know, QEMU could run according to wall clock, and you can run System C according to wall clock. And you can maintain some form of synchronization like that. So that quantum keeper blob in the middle is the thing which is responsible for determining exactly which one of these various different synchronization policies you might want to use. And there are probably half a dozen others that I haven't listed. There's at least 2 others that we use that I haven't listed here. I probably haven't given you enough technical detail to understand how this all works. That's probably the subject of another discussion. But did I at least answer the question about what happens and how?
Yes.
Okay, I'll keep going because time is getting short, and actually, yeah, we've still got a few slides to get through. I talked at the top of the call. I talked about cache models. So QEMU itself does not have a cache model, but what we've done is added an offline cache model to QEMU, which then propagates back into the CPU registers how many cache hits and misses you have. So this requires some some modifications into QEMU, some extensions there, which allow us to trap every single load and store, so that we can then feed that into a cache model, which actually we run in a separate thread, which then works out, you know, if this load and store sequence was to happen, then this would have been the effect on a cache. So that turns out to have, yeah, it has a speed impact, but it's like, it's not massive. It's like 20–30% performance hit. And what you end up with is the ability to yeah, you get some sort of cache statistics out of QEMU without completely killing performance. For an A53, we've got it. I mean, obviously non-random replacement and caveats apply, but we seem to be accurate to what the real hardware reports. So that seems to be pretty positive, and gives us the ability to model at least L1 caches very accurately. But people are no longer really that worried about L1 caches. People are more worried about L2 caches. So what do we do there? Concurrency is really the big issue, and particularly cache coherency is a huge issue here. So what we do is we run our standard L1 cache model. On the back of the L1 cache model, we feed into an L2 cache model. Now, the critical thing is we ensure that the processors involved are in separate host threads. So we are simulating the concurrency in the real device using the concurrency of the host. That's not necessarily the same concurrency, but assuming that it's a reasonable approximation, then we can build this sort of L1, L2 cache and see the impact of the cache coherency using the host's coherency to essentially kind of propagate the issues of cache coherency into our model. So that's kind of an interesting approach, I think, and means that, you know, again, we're not losing a massive amount of performance in doing that. We're able to run these things, you know, at reasonably full speed, yet we can get back answers about what the sort of cache coherency implications of the design would be. So that's kind of a new thing that I think is probably pretty powerful. Oh, Jakob's asked a question, but I saw a little bubble come up, but I didn't see what the question was. Yeah, Ola, do you want to?
Yeah, the question from Jakob was that the cache modeling, that would seem rather brittle, especially if the cores have different load levels or the host OS plays games with the scheduling.
Yes, absolutely, absolutely, and that's why I was kind of really pointing out the this is reliant totally on the parallelism of your actual host being somewhat representative of the parallelism that you're expecting on your guest. And that really may not be the case.
So follow up then, why not just run in time quanta here?
Because then you would need to work out exactly what the parallelism really should look like, and that's a much bigger and harder task, especially as we don't really know much about how many cycles things take anyway. So in order to keep the performance high and not to have to understand much more about how the actual CPU would perform, we can take this approach, which may give you kind of the global view. It's certainly not going to give you the accurate view, but it might give you the global view of how cache coherency is going to work in your application.
Just a comment again from Jakob saying that you could do this with a time quantum of 1,000 to 10,000 cycles. I guess you have experience of this, Jakob.
Yeah, I guess he does. Just a brief note that we also allow these cache model, and we also have a version of the cache model that sits in line. The advantage of that is that then you see completely correct TLM traffic, as opposed to in the previous model, the TLM traffic that we see out of the back here is exactly what you would see without the cache at all. So you see individual word accesses rather than seeing cache line fills. Some models find that to be a problem, and so yeah, you can put a cache model in line that hoses your performance. There are probably other and better ways of doing it, but they're not really QEMU related, so I'm not going to touch on them. A quick point on licenses before we get to the top of the hour. So QEMU is licensed under the GPL. It's actually GPL v2. You should know that just like any other set of models that you might have, you're more than free to license your own models the way you want to license your own models. And if you go to another CPU vendor and buy their model, I don't think they're going to be too happy if you just hack their license and send it to somebody else. So in principle, what you normally do is you either get a negotiation with that company or whatever, such that you can forward ship it, or they ship directly to your end customer. Basically, the same is true here. You can ship your parts of the model, and you should probably have a hole in them where the CPU is going to fit. And we would say that that's good because it means that your end customer has the choice. Maybe they already have an ARM model, for instance, and they would really like to use that. That's great. They can just plug the model in that they have. Otherwise, if they want to, they can download a QEMU-based model or whatever. The point really is, and it comes back again as well to why you would be interested in this stuff in SystemC. You should be writing your model independent of whether it's going to be using QEMU or ARM or any of the other vendors' models. Such that in the long term, you can swap out one and swap in another, or rather your customers might want to. So I don't think that, yeah, our view is that there's not a big issue with the licenses. And you simply ship, and you ship a little notice saying, go and get your model over here if you wish to. I don't want to take too many questions on licenses, but if somebody wants to ask, then I will. A quick note on downloads. I was really hoping that I'd have a nicely packaged up download that I could point you all at and say, go get that one from there. We probably have an ARM-based one and a Sci-Fi based one almost ready. We've just completely reworked all of our build infrastructure and everything else to use this thing called CPM for CMake, which I have to say, if you haven't used it, I'm quite enjoying it. It's quite good. But yeah, it's ripped everything apart, and we're only just getting to the point where we can put things back together again. As soon as those things are available, I will send a message out to everybody, and yeah, we'll post. I'll open up the Git at that point as well and post it. I'm not sure whether we'll post it onto GitHub. We might do that as well. We used to reflect off to GitHub, and then we stopped because the Git went in. It's a long story. Anyway, it will happen fairly shortly, I promise you. In the meantime, if you need something specific or you want to have a look at one of these models and you just want, to play around with it, don't hesitate to get in touch, and I can ship you, a Git from a link to the internal Git. The other thing that we're about to do, and we're working on at the moment, is connecting all of this up with FPGA as well. That's kind of exciting and interesting. And it means that, for instance, at the moment, we can have master or slave models in an FPGA on an Amazon node, for instance, communicating backwards and forwards through SystemC to QEMU. That's kind of an interesting aside. That's a completely different topic, but I thought I'd just put it in there as a bit of a taster, and I've already run out of time. So I'll stop.
Thanks a lot, Mark. I think that was one question or from someone that we didn't cover. It was loosely timed, and the answer is yes, I guess. This is all about loosely timed. Yeah.
Yes, this is all about loosely timed. Sorry, I was responding to David's little claps. Thanks. Yeah, it's all about loosely timed. Yeah, absolutely. QEMU is loosely timed. It certainly isn't cycle accurate or anything. We can talk about Gen 5 separately. That's a whole different ball game.
Okay, thanks a lot, Mark. We all give you a virtual applause, I'm sure. Let's see what we can do now. I can share, perhaps. So we are now going into the panel. And we have the panelists. I hope, Lucas, you are here.
Can I ask that the panelists put their cameras on?
Yes, I'm here and working on my camera.
Okay.
I am trying to share
I'll
my
try
screen.
to do.
Yes, so then we have Lucas, hello, and we have Rocco, and we have Laurent somewhere, I guess. Laurent, you're here?
Yes, I am.
Yeah. If we then kick off this panel by the panelists doing some intro talk for some minutes, just to get a flavor of where they are and why they are here, and perhaps if they have any expectations on this panel. And then after that, we take it from there and see what topics we want to dive into. So if we take it in the order from the slide, then we could ask you, Lucas, to start with your introduction.
Okay, I will try to share some introduction slides. Okay, you should now be able to see my slides, I guess.
Yes.
Okay, yeah, so welcome everybody. My name is Lucas and I'm here today with kind of two hats on. So on the one hand, I am a part-time employee at GreenSox, and on the other hand, I'm a PhD student at the Institute for Communication Technologies and Embedded Systems at RWTH Aachen with Professor Leupers.
Lucas, very quickly, something is blocking part of your screen.
Oh, okay, I think that's WebEx. Better now, I hope?
Yes, mostly.
Yeah,
thanks.
Okay, I'll try like this. And yeah, so I'm interested in the boundary between software and hardware, and exploring this boundary with transaction level modeling and simulation. And I'm also very interested in open source tools, for example, QEMU. Yeah, but not limited to QEMU. If you share any of these interests, feel free to scan the QR code and follow me on GitHub or add me on LinkedIn. And yeah, now I'm going to talk a bit about my hopes and expectations for this panel. So, well, this panel is about SystemC modeling libraries, and I would just very much like to understand the different use cases and viewpoints for such modeling libraries, and also get an overview over solutions that exist. And I guess the goal would be to find some alignment on requirements for a modeling library that we can all use together, so that not everybody has to re-implement everything and reinvent the wheel over and over again. And of course, I would also like to see some discussion about standardization opportunities in that regard. Finally, one such modeling library is the virtual components modeling library, which yeah, comes out of our institute at RWTH and was started by a former colleague of mine. And yeah, this modeling library is for loosely timed SystemC simulation, and it's basically built on top of the TLM standard, and it consists of different parts like we call them, there's VCML authoring, which is just some abstractions that everybody needs for building SystemC TLM models, such as register modeling primitives or some extended sockets. We have something that's called properties, which is similar to CCI, I think. And also we have some common extensions for things that everybody needs, like, for example, exclusive memory and stuff that helps you with timing annotation in your models and testing. And on top of these modeling primitives, we build the models. So this modeling library is all open source. You can scan the QR code. It's licensed with Apache license. And we have a bunch of models in there already, like bus models, memory, interrupt controllers, QArt, frame buffer, SDHCI, and a bunch more. And to use these models, it comes with a bunch of tools. For example, tools for logging and different backends for the UARTs and Ethernet models that allow you to redirect the output and the traffic. And also we have some debug implementation there as well, so that you can connect GDB to a processor model that is written in VCML. And this is it's just one example of what such a modeling library could look like, and is kind of our viewpoint on that topic. Yeah, I guess that's it from my side.
Lucas, then let's move on and ask Rocco for an introduction.
Okay, so I guess it's my turn. So let me also try to share just a few slides. Okay. So hopefully you can see now a different set of slides.
Yes.
Okay, very good. So my name is Rocco Jonak, and I'm working at Arteris. I kind of represent here also basically two people at once, myself and Aitjench from Minres GmbH. And we have been working together at Arteris to work on various modeling tasks. And already even before in other projects, I actually have been working with Ike and with Minres GmbH. And we found actually that in various of these projects we came across similar issues, similar tasks that we had to do, and we always felt that you sometimes kind of reinvented the wheel, just like Lucas already said. You have very common tasks. And that's where we started actually also to look around for something that I would call a productivity library. And we found actually remarkably little there in the market. And so I feel that it's a very good opportunity that this organization now picks up that topic, and we can maybe discuss a little bit whether more people feel like such a productivity library would be needed. I don't want to talk too much there actually about the productivity library that we are currently using, which is called SCC, SystemC Components Library. It is also an open source project. Maybe during the discussion later we can go into a little bit more details, but we basically see that there is a number of common tasks around register modeling, memory modeling, logging, infrastructure tasks, basically also, of course, parameterization, which we feel could be really done in a very generic way, and would allow you then maybe to focus on other tasks. So we are not focusing actually in SCC on models themselves. We are more focusing on infrastructure that would allow you to write models more quickly, basically. Okay, I think with that maybe we leave it for the introduction at that, and maybe during the discussion we can go into more details if needed.
Yes, thanks. Then we move to Laurent.
Okay, so let me share my screen as well. Do you see my slide?
No.
Interesting. Sounds good now, I think. Okay.
Yes.
So I'm Laurent Maïcontos, working with ST for some years now. And so I'm heading the SystemC modeling activities within ST. I've been active in a certain number of projects within ST, and I've been contributing for a while to SystemC standardization activities. So I would like to start this discussion from another perspective. So I will not discuss about what would make sense as modeling libraries, but just asking the question about at the end, why do we want modeling libraries, and what should we consider when we develop or when we look for modeling libraries? So I try to create a kind of radar diagram considering the various dimensions that probably make sense for people who need to have or develop such modeling libraries. So obviously, interoperability is a key requirement. So we need to consider model-to-model interoperability, such as the one provided by the TLM standards. Model-to-tools interoperability is obviously very important when we develop modeling libraries. So CCI is one step in that direction. But there are also many other dimensions that we should consider. We should consider how these modeling libraries can help for model quality, help for portability across operating systems, compilers, versions of simulators, and so on and so forth. Companies have usually modeling guidelines. So how these modeling libraries can help to conform to company modeling guidelines. When I use modeling libraries, that's to improve my productivity. So we also need to consider the cost effectiveness of these modeling libraries. Few experts might be very comfortable with very advanced libraries, but at the end, several modeling engineers might be involved, and we need also to consider the adoption and the learning curve for such libraries. Productivity, of course, is a key criterion for selecting the modeling libraries, but we also need to consider that the needs are evolving very quickly, and we need also to provide support for specific needs or emerging modeling needs. So overall, then I can imagine that we could create that kind of diagram for various modeling libraries from various providers, vendors, and so on and so forth, or open projects. At the end, what I would like to see is the library or the libraries, because I'm not sure only one library would be enough, that maximize the support for all these dimensions. So yeah, then I think we can discuss further on a few other topics. I will come back to that in the discussion.
Yes, thanks. Now we should figure out how to start. I think of this as, I mean, there are two dimensions. I think of these libraries. One is the actual models, and one is the actual simulator with all the building up the simulator and logging and debugging and stuff. So I don't know, perhaps we should start in one of those dimensions. And if we start in the model dimension, just to see if you want to comment on that, why this need occurs and what is missing then in SystemC and TLM, and what has driven this development of these model libraries, and what could then be learned from this and perhaps harmonized or brought back to the Accelera for improvements. I don't know if we start in the model angle. So panelists,
Yeah,
please comment.
Okay, so let me start.
Yeah.
we have all been exposed to the TLM standards for more than a decade now. And if we look back to the TLM2 standard, for instance, we see that to be fully compliant to the TLM2 standards, we need to implement a very huge number of rules. If I'm not wrong, I think there are about 500 rules to be implemented or to comply with to be fully compliant to the TLM2 standard. I cannot imagine that each and every modeling engineer has the full detailed knowledge of all the rules that needs to be implemented to be compliant to a standard. So having a modeling library that provides a user layer on top of the standards to simplify the way models are written, to be more efficient, more productive in writing and developing the models is certainly a key asset to enable the deployment of SystemC-based activities. Unfortunately, the TLM2 standard, as we all know, is not enough. Lots of people have already introduced the need for other kind of protocols for interoperability. In the CCI group, we have been discussing parameters for so many years, and so on and so forth. So I think that modeling libraries are nice to speed up the deployment and the development of the models. And as we as the other panelists have already said, there are modeling primitives that everyone is implementing again and again. And so this totally makes sense to commonalize what can be commonalized, kind of commodities that can be defined in a common way, and then maybe with various implementations behind the scene, but at least having a minimal kernel that makes sense for everyone.
Yeah, maybe to add to this, I think there are when we talk about models, there are two different things. So on the one hand, it's building models and having modeling primitives. As was already said now a couple of times, everybody seems to rebuild the same primitives over and over. But maybe it can go even further. So I think there are just some standard models that everybody needs. For example, such a thing as a UART. There's not really, I guess, a lot of value in keeping this private, because why should everyone reinvent a UART model all the time? And I guess you could even go so far as to make certain base models that everyone needs more or less publicly available, as we already kind of do. And then you can focus on the development of really the core IP models that you maybe also want to keep private, because that's important for the business.
So maybe if I can chime in there a little bit, to me, actually one interesting thing is there that I always feel that LT models and AT models are very different in that respect. I agree that for LT, there is a set of standard models that seem to be always used and let's say provide some common, not very complex functionality. On AT models, I'm somewhat skeptical that it makes too much sense to provide their models, because everybody implements their models a little bit differently. So I think we have to distinguish there a little bit, but maybe with the idea of having there even several libraries available, one focusing, on a certain aspect, because yes, I do agree with Laurent that maybe not one library will really meet all the expectations. One thing that jumped to my mind when you brought up the question is, of course, one thing that also for AT is from my point of view, a very common thing, and that over and over again causes issues, at least in the context of the models that I'm working with, is the interfaces, the TLM interfaces that are specific to standard protocols. Of course, the AMBA-based protocols are, I think, at this point, very, very widely used. I don't want to put a percentage on there, but from our point of view, it is a very, very high percentage. So it is to me, actually a real issue that we have no common implementation of the extensions. And when I talk about extensions, we have to really make sure that extensions both for LT and for AT will work. Specifically for AT, there are some concerns. Of course, as you can guess, we have in the SCC tried to address this issue, but these libraries live, of course, of common usage of those. So maybe one of the questions would be to me, of course, also to other users, do they also see issues with simply the fact that if we cannot even agree on what the interface is, then the model itself doesn't matter too much anymore.
Well,
Yeah,
I guess we should distinguish between the extensions that could be provided by a certain vendor, because these extensions are tightly coupled to a certain hardware IP or hardware protocol. And there I would expect that the IP vendor is offering the corresponding extension. And I don't see why the community shall take over to deliver such extensions and under which conditions and liability.
I sort of agree there with you, Laurent, but do we have anybody from ARM online?
Lol.
Okay, so the common problem there is that simply there is nothing from ARM, at least nothing that is consistent over all the different protocol variants and the different abstraction versions. So now the practical problem is, what shall we do? We all go off, do our own thing? I don't know.
As customers, I think the customers shall also, the customers, if they see a value, if they see an interest in that, the customers might also ask the provider to deliver such extensions. If there is not enough value so that the customers do not ask, then that's probably useless to develop that.
So do we already kind of agree that we need multiple libraries, at least one for loosely timed and one for approximately timed?
I don't know. What would be the content of these libraries at the end?
Yeah, I mean, we focus much on loosely timed modeling because this is what we primarily do. But of course, approximately timed modeling is also a large field. But it feels like that these two are somewhat disjunct, and maybe therefore, as Rocco already said, it makes sense to separate out different things for the different modeling styles. And if we speak about extensions in the loosely timed modeling style, I mean, if you look at an extension, for example, exclusive memory accesses, if you want to do them via blocking transport, this is probably something that everybody wants to do and needs to do. And then maybe it makes sense to agree on a way on how to do it.
But then I would claim that this is not a modeling library. That's an extension to the standard. So
yeah, I guess
I think we need also to distinguish what is useful in terms of productivity or efficiency in terms of model development, and the modeling libraries might have a perfect fit to that, as opposed to what is missing today in the standards. And if we want, as a community, to implement extensions or things that are just missing in the standard, then we are just talking about we need to extend the standard. We do not need a modeling library for that.
I mean, so Lucas, you started with the question whether we think different libraries for different models. To me, it seems like for models, I would definitely claim that a set of different libraries is probably a good approach, because I think different customers may have different views of which models are really helping their productivity and which are maybe less important. For the infrastructure, I would claim that most likely the same library might be useful. So I guess we haven't Ole tried to kind of split it a little bit into models versus infrastructure. So for the infrastructure, which is to me actually almost to me a little bit more the target of a productivity library, there I would claim that the tasks are typically the same and could be used across 4 models. I would tend to believe that different libraries might be the better approach.
There is a comment in the chat, bring up the distinction between common components and infrastructure which wraps the standard. Is this related to what you said, Laurent, about this? Then we are not doing libraries, then we should change the standard.
Yeah, I think that if we come back to the TLN2 years, we faced a lot of difficulty to converge on the standards because at the end, people had different expectations, different needs, different perspectives. And as usual, the standard was the, let's say, the minimal set of features we were able to agree upon. And as usual, that's not enough. So it's about the semantics. What do we want to model? How do we want to use the models? For which purpose? And here I believe that various companies have different expectations or different guidelines about that. So that's why, let's say, the way the standards are built are sometimes a bit frustrating because we never achieve the goal of getting full interoperability or full features. At the end, what is important is interoperability. Where we are not talking about interoperability, we are just talking about productivity. So there are various ways of implementing that. Companies might implement their own libraries to be more efficient. Some elements might be shared because they are of common interest for everybody. But we need also to be very specific about what we would include in such libraries, because I hear for years that we want to have a library for registers. I can imagine that defining what would be the content of a library to model registers would also take years if we want to cover each and every need for each and every company for each and every model. Then for sure, we can have a limited subset of functionality, but that would be useless.
But I think where it might really become interesting is when we talk about the sockets, the interfaces, and especially in combination also with extensions, because this is basically where interoperability is required. And I think there is with the CCI there is some push to improve interoperability, maybe also in this regard. But I guess that would be maybe the first thing to focus on.
Yes, so as you said in the Accelera Common Practices Working Group, actually there is some interest in trying to find solutions for that. But yes, we would welcome, of course, also more people to work in that, bring their opinions to the table. I agree that also the ultimate solution would be, of course, if the actual the person that specifies a standard, in this case ARM should be actually in charge of specifying something. But if they don't do it, the issue still remains in the market. So that's why from my point of view, it is worthwhile as part of this effort. There's several topics that can be addressed, but I think from what I'm hearing, if you really want this thing that addresses everything, I almost believe you will have to go with a set of libraries, because I'm doubtful that you find in different companies with all these different requirements really a common set for all these things. The registers are, I know, a very controversial topic. It is amazing how many hours you can spend, or probably days, weeks, to discuss that topic. So why not maybe having several libraries that implement that? Of course, you also need to worry about fragmentation, but on the other side, what I'm seeing right now is that different companies have their own implementation, but then for smaller companies, it becomes very hard to actually find something. So having something in a Accelera playground would be, to me at least, an interesting thing to get started, and to maybe to have also other people then encouraged to provide their implementations and to say, hey, I need this additional functionality in my registers, and not just continue to discuss that rather abstractly.
It all depends on where we want to put our efforts. As a standardization body, I think that where we should put our effort first is about interoperability and defining the APIs that improve the interoperability. For instance, instead of implementing registers, to me, it would make much more sense and much more value to define the API to support register inspection, regardless of the way the registers are implemented in company A or in company B. So I can imagine that people would like to get for free modeling libraries to create their registers. But at least from my perspective, I would be much more interested to see progress on inspection. So defining the APIs to have the capabilities to understand register structure, register values, bitfeed values from any tool towards any model, compared to spending efforts in developing yet another register modeling library.
A comment on that, Lon. I mean, that is exactly what we are talking about right now in the CCI working group, to start to talk about this inspection and how to get such an API. And we have also concluded, like you, that discussing how to implement the actual register is not fruitful, because there will be so many ideas on how to do it.
But don't we think that maybe one doesn't have to exclude the other? From a standardization point of view, I agree. The API is more important. A modeling library can be, for instance, something that uses that idea, or that implements an example of that idea, is kind of a playground. And a modeling library, to me, is also something where we don't need to go right away for a formal standardization. Maybe we want first something where we try some ideas and see what actually has hold in the marketplace. Well, what does it help if I go for standardization of something that then ends up not really being used? I think modeling libraries could potentially be a way to try to see if maybe an idea, and we're also discussing some ideas in the common working group, common practices working group, where maybe such having some examples for implementations of these ideas would bring it much closer to a user. So having maybe daring to use modeling libraries more as something to try things, which is of course for standardization maybe a little bit a different angle.
Try just a thought here. I mean, now you have experience of creating your libraries, and you might have users using your libraries. I mean, if you want to comment on the libraries you have, what is the best thing with them, and what models in the libraries are the most useful ones? I mean, one said here in the chat, what do people want? Do you want UARTs, or do you want register files, or do you want Ethernet controllers, or is the interface between the models much more important than the model itself? So if you can comment, panelists, on your own experience from your own libraries, what you think of as success aspects of your models. What has been the most successful model to put in the library? What has been difficult to sell, so to speak? What are you most happy with?
Yeah, I think we need to distinguish when we create a model of an SoC, for instance. An SoC will be composed of some CPUs, some hardware blocks, interconnect, some commodity blocks. My take would be that the IP owner that sells the IP shall also provide the model for the IP. So whether it is a CPU or hardware accelerator or whatsoever, there should be an ecosystem of models that correspond to the various IPs that are on the market. Now, there are also a certain number of blocks that are required, but that have, say, little value, and nobody is really ready to spend effort to deliver and maintain such models. So I suspect that most of the companies have their own portfolio of commodity models that they have built and they maintain and they reuse from projects to projects. But to me, that's a very limited set of IPs that are listed here compared to the effort of developing, let's say, the models of the real IPs that have real value. So I'm a bit questioning let's say, the benefits of sharing these models, because at the end, that's in my view, a fairly limited set of models.
Mm-hmm.
But isn't there also some cost associated for the upkeep of these models? I mean, if you, as you say, probably every company has implementations of some standard models, and they have to be maintained. I mean, if there's an interest in coming maybe to a common understanding of how to build models and how to connect them, maybe it makes sense if everybody just basically maybe just open sources or shows their how they build basic components. I mean, then in the end, maybe there can be some unification from that, and also in the end, it probably saves money for the companies because they don't have to pay the upkeep for these standard models that are, as you say yourself, of little value.
I'm not so sure, because I suspect that every company has their own modeling strategy, their own expectations, guidelines, requirements in terms of modeling, in terms of interoperability on top of what is already defined in the standards. And to take a very simple example, just the way you would integrate a model coming from a third party into your build environment makes some effort. So I'm not sure that at the end, putting on the table all these models, regardless of all the constraints each company has, would be worth the effort.
Mm-hmm.
Do you want to support Linux? Do you want to support Windows? Do you want to support another operating system? How do you build that? Do you integrate in CMake, in your own handwritten makefile, in some other way of generating your build environment, and so on and so forth? So all these questions that are probably not so interesting at the end, but they create real constraints and real pain for model integration.
Yes, actually, exactly for that reason, since Ateris models are models that are widely used and widely integrated in many different companies, also several companies of participants here. And that's why, quite frankly, the SystemC components library in the context of Ateris doesn't focus so much on the model itself, but on the infrastructure. Mm-hmm. And I think that indeed makes for the model integration has a much bigger differentiation. The model, yes, I think Ateris has, of course, models that they will never fully open source. But nevertheless, having an underlying infrastructure which uses common constructs, common locking mechanisms, that has, from my point of view, a lot of value. And there, if we could agree across organizations on different common infrastructures, I believe that would help. Build system is a very complex subject because everybody has, sometimes for legacy reasons, for all kinds of reasons, different constraints. But I believe even libraries like CCI would really benefit if we have really libraries that are built on top of CCI, use these CCI parameters, so that really everybody underlying then uses the same constructs, which would also even help tool vendors that then could come in and rely on the same underlying mechanisms.
I think it would also maybe further adoption. I mean, if you have some examples, it's that's always useful. And yeah, I think if we would yeah, publish some of these yeah, models of lower commercial value, even, I mean, I acknowledge, of course, that there are some constraints to this as well, but if that would be done, then first of all, there would be an understanding of how these underlying modeling primitives are implemented in each company. I don't know, maybe that's also something that some companies want to keep secret, but let's assume that could be done. That would help, yeah, understanding what's actually needed, and also for people who yeah, just start looking into SystemC, I think it would be useful to start with some simple building blocks that they can already use and continue from.
You mentioned the infrastructure there, Rocco, so perhaps we should, I mean, we have talked about the models, and there are several comments here in the chat. I just want to see if I want to refer to some of them. I mean, implementing the actual model is one thing, and then the interface is another thing. Are we looking at building a Boost library for SystemC? Is that what we are talking about? Perhaps the success of Boost could be inspiration. And then having such libraries, be it for the actual models or for the infrastructure, Jakob says there is a much better way forward than trying to standardize. And I think that's an interesting comment, because we have had in SystemC Evolution days, for example, at several occasions, discussions about, oh, let's standardize I2C and let's standardize Ethernet. But those discussions never came to any conclusion. So having such things in libraries is perhaps a much better idea. But talking about the infrastructure, Rocco, your experience is that the infrastructure is really something that people have picked up and found useful. Can you elaborate on that?
Yes, certainly. There's really a lot of what I would call relatively boring tasks around logging mechanisms, having common formatting for logging mechanisms, having ways to turn on and off logging mechanisms based on different log levels. Also, the whole topic of tracing signals in your model, having to go in there and to declare everything yourself seems to me like a very tedious task. Also, the topic of tracing of transaction level tracing is something that we are doing more and more, and trying really to standardize a little bit more on. And so far we are seeing pretty good adoption on that. So on actual models, it is specifically in the AT realm. It's probably a little bit more difficult to see how you can come up even with a common model, because it is so implementation dependent, and yeah, part of it is also let's say how fast you can implement a certain functionality. And in AT you are talking about how many cycles you need for a certain functionality that can be sometimes the company's secret sauce. So there I'm a little bit more pessimistic. In the LT area, this is potentially again completely different, because there maybe the functionality is a lot more common, but yes, I would frankly focus a lot more on infrastructure tasks. And yes, I think the idea of having it in a library, call it the boost of SystemC, I don't think that's a bad idea or bad way of seeing that, would be perfectly fine, and then seeing if adoption actually requires any further standardization.
Well, I think all the difficulty at the end is for companies that are integrating various models from various sources. If everyone has his own boost-like library for his own tracing mechanism, at the end, it's a nightmare for the guy who is integrating all these models together. So I would like to be a bit let's say provocative on the topic, but either we have one library that is shared by everyone, so at the end this is a de facto standard, and it might work, or if we have several libraries that guy from company A is using library 1, the guy from company B is using library 2, and the third guy who is integrating both models together, there is no way to proceed. So at the end, in my view, we should still consider the integration step as critical. And so I would still advocate to finally converge towards a standard for this kind of features. Now, if having modeling libraries is a nice way and pragmatic way to progress towards a common understanding of what is needed, what makes sense, and how this should be implemented, that's fine. But at the end, we also need to be very, let's say, cautious on the proliferation of libraries that would do the same kind of feature, but yet in a different way, because at the end, integration is a mess.
Yeah, I agree with you, Laurent, what you just said. I'm just wondering, what do you think would be a good place to start with this? So if we wanted to start today to move into that direction, what would be an easy step to take?
Again, register inspection is probably one nice step. I agree with Rocco, tracing and logging is also important. So offering such capabilities in a library is probably very nice. And not too much controversial, I would say.
And commenting on this tracing and logging from Jakob, coming back to the tool, implementing things that are tools versus talking about interfaces and letting the interfaces move into the standard. And then we have a boost comment from you, David, that yeah, there is an interesting analogy that boost is really something where things live before they move into C++. So perhaps we can mimic that and learn from the boost experience.
I like it.
Yeah.
I like the idea.
Yeah.
I have two comments there. Indeed, C++ is evolving quite rapidly. Today we are discussing about realigning SystemC on, let's say, C++ 17th, I guess. And there are much more features in the recent C++ standard compared to C++ 11, for instance. So indeed, there is already a trend in the underlying language, and we should monitor the evolutions of the underlying language to facilitate the implementation of SystemC models.
Yeah, sure.
Now about vendors. Unfortunately, we do not have the one of the major EDA vendors on board in this panel, but that would be interesting also to understand what is their view on modeling libraries. I know some of the vendors offer their modeling library. This also creates some constraints in terms of portability, interoperability, and so on and so forth. But indeed, we are at the boundary between tools, implementation of libraries regardless of tools, and standards. So having a Boost-like approach is probably very nice, because it might be the right way to go to avoid too much commercial difficulties.
Time is ticking a little bit. It's 17:52 here. Perhaps we should just see if more people from the audience wants to comment or speak or add input. What do you think of this discussion? Do you want to add? What would be most important for you to have in a library if we ask everyone in the meeting? Anyone wants to comment?
I think the distinction between infrastructure and quote unquote non-controversial models is an interesting one. Degree to which it would be helpful to have a well-written memory, a well-written bus, a well-written UART, and probably not an awful lot more than. Yeah, we can always say, well, that's not the way we do it in our company. That's true, but probably there are a lot of companies out there that don't do anything at all yet, for whom a set of quote unquote relatively well-written models would be at least helpful, maybe. Equally, I think there are components that you could add to the existing standards that don't need to envelop the standard, that don't need to develop the standard, just use the existing standard to show how the existing standard should be used. There, I think there's some value in providing some useful code. This is how you write, here's a model that correctly used CCI parameters. Then on the other hand, yeah, there's another discussion, which is, well, and actually, Laurent, you brought it up in your spider diagram, the degree to which it is actually useful to abstract away from the standard on the assumption that the standard is going to move in a kind of a boost-like way towards whatever fantastic new idea you've got. I'm not so sure and that's kind of the infrastructure idea, right? That I wrap up the standard, I make it better somehow. And I think that's where there's kind of some danger in the infrastructure line of doing this, that if we go down that road, then we are definitely suggesting that this is kind of a pre-standardization attempt, and I'm not convinced that we are able to do that. I don't know.
What about this standardization of protocols? If I remember this SystemC Evolution Day, the discussions that were not coming to conclusion is, does anyone have had any good experience of such commonalities? I mean, have you seen, oh, now they are using our I2C payload extension. Nice. Perhaps more people can start using it. Have anyone seen any positive signs on that protocol horizon? If I call it like that. I mean, a common Ethernet class or something like that.
Nope.
I think that to make progress here, we need to have more system houses or tier one companies involved. Because at the end, all the people who have been active in the standardization in the SystemC topics are focused on system on chips or this kind of stuff. Now, when we are talking about Ethernet, I2C, SPI, CAN, and so on and so forth, we are talking about protocols that make communication between various chips to create a more complete system. And I can imagine that the tier one would be the guys who would drive these discussions because they are the first users of that. Whereas in the group here, people are probably more focusing on inside the chip compared to off-chip communication.
Yeah, I mean, Arteris has there a little bit a stake kind of in both sides because the main focus is of course on chip communication, but we are clearly seeing there also a move to chip to chip, die to die kind of communication standards, which are building up on the same or very similar communication mechanisms. So I agree. We need the people who are really having those models and who want to integrate different models to be active here to drive this. From a practical point of view, I can only say that from an IP company point of view, as Arteris is, you have to decide to basically go with if we have an AXI, ACE, CHI interface, we will do our implementation, and if there is no standard implementation out there, we will tell the customer, well, that's what it is, please deal with it. This is not always the best way, but to make progress, it has to be really the system houses, if they have problems with that interface, maybe interfacing then to other models, they will have to be there also active and driving that.
Yeah, we have a comment from David here coming back to this boost model. So yeah, interesting.
Regarding that comment that was posted in the chat, maybe Rocco mentioned that, I think, in his introduction presentation, that when they started SCC, there was not much around, and in terms of other libraries. And I wonder if it might make sense to have a common place where there's at least a collection of references of what actually already exists, so that people can take a look at the things that are open and maybe take inspiration from them. I think that would be something that's very easy to set up.
Yeah, I agree.
I mean, we could, in this community, we who organize these Fikas, we have the ambition to reinstate the SystemC.org URL. Right now it's just coming soon, but someday there might be some content, and then we could chip in and help to put like a directory of libraries that we have talked about in this meeting, and to help people find stuff. And we are some kind of Accelera affiliated things, so that people can find SystemC.org, and from there they can move on to other libraries. So that could be something for us to think about, definitely.
One comment about that. I think we have been suffering for years about low level of contributions in the standardization working groups, because people didn't have the bandwidth to be very active in there. I'm very happy to see that there are lots of intentions to create a community, to create modeling libraries, to have dynamics on these topics.
Yeah.
I'm just curious to understand how active people will be to develop, maintain, deliver, train, support people interested to use these libraries. because at the end, this requires also a significant effort and significant bandwidth to keep things up to date and so on. So that's very nice. There are lots of good intentions, but at the end, people need to put their hands on the code and deliver and support.
Yeah, sure. I mean, there was a comment here about students, and I mean, there could be commercial interests for a company to invest in such a community software, because when young people wants to work at Ericsson, the odds that they have seen SystemC is bigger than if Ericsson does not invest in such a community. So that could be a commercial incentive to put money on these open source things from different companies. For example, from a recruitment perspective, because sometimes when we put out ads and we say, oh, we want some SystemC developer, and there are so many young people who have no clue what we mean. I mean, okay, we of course say C++ as well, but there are many young people who don't even know what C++ is, because they all program in Python. So yeah, this is also interesting.
In terms of building the community, as far as I'm aware, there is this SystemC forum from Accelera.
Yes,
but like, not as far as I know, there's not many other things, right? So the forum is about the only place where you can go to find things, if I'm not mistaken.
And you can come to these Fikas.
Yeah, and you are. I mean, we have participants here, right? So we should be happy for that. Yeah.
Maybe then a sticky thread in the forum would be a good place to start off for collecting things. I mean, if there is already a community platform, then maybe it makes sense to use the community platform to start a collection of what exists and yeah, where people can start.
Time is running. It's 18:03. Perhaps we should conclude. This was our first panel. I think we had some good discussions here. I'm thinking now if I could capture the chat in some way. I need to figure that out, but I can do that after we close down. And you in the panel and Mark, please send your slides, and I can bundle them together and put them on the website.
Sure, and somebody on the chat is asking where they can get hold of a QEMU and a SystemC together. If you just drop me an email at mark@greensocks.com, I'll let you know. I'll point you in the right direction.
Okay. But then let's close this Fika and hope to see you all in SystemC Evolution Day, which would be the next event of this style. So thanks a lot. Special thanks to the panelists and the speakers, and to the people and to everyone who has put in comments and questions in the chat. Thanks a lot. See you later.
Thanks.
Bye.
Thank you. Bye-bye.
Bye-bye. Bye.
Bye.